Guys, so today we're going to talk about the packing factor of diamond. Um, this is a no BS guide. There's some things I'm assuming you know. I'm assuming you know what a primitive cell is. I'm assuming you know what a diamond structure looks like. I'll still make a little bit of diagrams, but I just want you guys to know. So, packing factor of a diamond. Now, packing factor is just the volume of the number of atoms divided by the volume of the cell. Now, volume of a cell in any cubic cell is just A cubed. Volume of the atoms, on the other hand, is the number of atoms multiplied by 4 over 3 pi r cubed, where 4 over 3 pi r cubed is the volume of a sphere, r is the radius of one carbon atom in a diamond lattice. So now, if we were to put both of these V cell and V atoms into this equation, what we end up getting is the packing factor is equal to the number of atoms. Now, the number of atoms, I actually should write this out. The number of atoms, since I'm assuming you know what a diamond structure looks like, there's 8 atoms. So that would be 8 times 4 over 3 pi r cubed. All right. Now, if we were to write this out now, we get 8 times 4 over 3 pi r cubed over A cubed. Right. Now, the problem is that we don't know the relationship between R and A. We actually have to find that relationship because this packing factor is supposed to be a number, and no variables inside here. So we have to determine R in terms of A. So I'll move this down a little bit. Now I'll try to write out what I'll try to draw out the diagram. And I'm assuming you know mostly what it looks like, so I'm going to draw it out super basic, so there's no confusion, right? So here's the back side of the lattice. Here's the front side of the lattice. I mean the bottom side. I'm not drawing anymore. I know there's like a side on the right here, left here, and the right here, and the top and the front. I'm not drawing those, right? So I'm just assuming here. Now, we know that there's a carbon atom here, and then there's a carbon atom here, here, here. Well, I don't care about those three. I'm only looking at this one right now. And we know there's one up there as well, and up here too. Now, we know that it makes this weird shape where it goes up, there's an atom there, it goes down, there's an atom there, it goes up, there's an atom there, and then it goes down, there's an atom there, right? Now, let's actually not consider this one, but this one right here, right? This one and this one. If we consider these two atoms, we know that from here to here, and on the other side it's similar, where this actually goes all the way across as a diagonal, and that diagonal is, if we use Pythagorean theorem, what we get is a cubed plus a cubed, a squared plus a squared plus a squared, which is just the sides, is equal to that side. And then if we were to figure this out, what this was, what we end up getting is that side is equal to root 3a. Right. So if we take a look at this, what we end up finding is, excuse me, that this distance right here from the one atom to the other atom is just 1/4 of that distance right there. So that'd be 1/4 root 3a. Right. Now, move this down a little bit. So we're only considering now these two atoms right here. So I'm going to draw them out again. So here's one atom, and then from here, here's the other atom. We know that this distance is going to be one radius, and these are not to scale, but one radius and then another radius, so that would be 2r. There's two radiuses here because there's two atoms. And then we know that if we were to take a look at the distances otherwise, going left or going right, going back and going up, drew this a little wrong, so if going back, going this and going up, ignore that line. If we do this, what we end up getting is this is 1/4 the distance of A, going back is also 1/4 the distance of A, and going up is also 1/4 the distance of A. Now, I'll actually draw this a little better. I feel like it's pretty bad. So, this one atom and then to the other atom, that distance is 2r. And then he goes this way, that way, and then up. That's fine. Right, so this just makes a triangle. And we know this is 90 degrees, and we know that is 90 degrees as well. So what we end up finding is, again, this is 1/4 A, that's 1/4 A, and then going up is also 1/4 A. So if we use Pythagorean theorem, what we end up getting is √3 over 4A is equal to 2r. And now if we solve for r, what we end up getting is r is equal to √3 over 8a. Now that's important. Now because if we go back up here, we find that if we can just plug it into our our packing factor, we can plug in r with what we just got, and then we can get rid of the a cubed and a cubed. So if we do that, what we end up getting is packing factor is equal to 8 times 4 over 3 pi, and then instead of writing r cubed, I'll write this cubed, which is √3 over 8a, all cubed, divided by a cubed. Now if I were to distribute this 3 into here, this would make it a cubed, and this would make it a cubed, so that would go away. And then what I end up getting is just a bunch of numbers, which if I put into my calculator, that's approximately equal to 0.34. And that's your packing factor of a diamond.